local variables, right? It doesn't have any memory implemented variables, so this turns out to be emp, and so on. Okay, so this is our proof goal, the Hoare triple, precondition, command, postcondition, and we have some things above the line. Sigma and P were exactly the things bound by that quantifier, the with clause, and they've been introed above the line here. All right, now, and let's put back the abbreviations. Why do we abbreviate the postcondition and all the commands but the first one? Well, we're going to do forward proof, forward symbolic execution of the program, where the symbolic states are assertions. And while we're doing forward proof, we don't want to bother looking at the statements we haven't gotten to yet. They would just get in the way. And we don't want to look at the postcondition because we'll worry about the postcondition when we get there. Let's just look at the parts of our program and specification most relevant to the current proof goal. And so abbreviate Simax does that. And what is abbreviate? It's just the identity function with very aggressively implicit arguments. Okay, now, this tactic, forward, says, find a proof rule that's good for applying to this kind of statement. What is that kind of statement? That's an assignment statement, right? So forward will find the right proof rule for assignment, and it will apply it to that statement. And so if I do forward, notice this state has v gets p. That was the second command in the function body. So forward has moved us past the first command, and now this precondition is the precondition for the rest of the function body after the first. So in other words, it's the postcondition of the first command. And notice it's just like what we had before, except this extra fact is in here, that the variable w now contains a null pointer. And in C, you know, a null pointer is just the cast of 0 to a pointer type. Okay, so let's go forward again. V gets P. And so now that's the postcondition of V gets P. And now there's another fact in the locals that the variable V contains the value P. And now we're at the while loop. And if we say forward, it would complain. It says forward failed. Use forward while with an invariant to prove this loop. The program logic does not figure out your loop invariants for you. You have to write the loop invariants. So we use, where's my cursor? There it is. We use forward while with an argument that's a loop invariant. And this loop invariant is exactly what I wrote down for you on the slides. It's that there exists a sigma 1 and a sigma 2. So we'll do forward while. Forward while leaves 4 proof goals. There's the 3 that you would expect from pencil and paper proofs, and another one. Okay, so the first one that you'd expect is that the current assertion implies the loop invariant. Okay? The second one is the current assertion is strong enough, the current assertion? Yes. The current assertion is strong enough to guarantee that the loop test doesn't crash. No, I take it back. It's the loop invariant is enough to guarantee that the loop test doesn't crash. So that's the one that, you know, Tony Hoare and John Reynolds would have left out because they weren't paying attention, which is that if your loop test does crazy things and has undefined behavior, then your program crashes, and you have to prove that the loop invariant is strong enough to guarantee that won't happen. The third assertion is that the function body preserves the loop invariant. And the fourth is that from the loop postcondition, you can execute the rest of the function body with its specification. So let's look at proof obligation number 1. The current assertion is enough to prove the loop invariant. Well, this thing here is our entailment turnstile, and to its left we had the current assertion, and to its right we have the loop invariant with 4 existentials. So we need to demonstrate values S1, S2, W, and V that makes all this satisfied. And since V contains P right now, we had better instantiate V with P. And W contains 0 right now, so we better instantiate W with 0. And 0 represents the empty list, so we better instantiate S1 with nil and S2 with sigma. And that's what's going on right here. Capital E exists. We'll instantiate separation logic existentials that are to the right of the entailment turnstile, and we will use the empty sequence of values, sigma, the null pointer, and P. Null val is just an abbreviation for the integer value 0. Okay, so this is the current proof obligation with those existentials instantiated. When you have one of these entailments, what I call a lifted entailment, prop, local, and sep, and what I mean by lifted is it not only can see memory, it's a predicate on memory, but it can also see the local variable state, what's in the temporaries. And since when you have a Hoare triple, the local variable state in the precondition might be a different one than the one in the postcondition, and you have to reason about how it changes. But in entailment, the pre and the post is always over the same state, so it's easy to factor that out. There's a tactic called entailor-bang that is good at simplifying these messy-looking entailments and proving the parts that it can prove and leaving the residue for you to prove. So we will call entailor-bang, and it says, okay, I proved everything except this part. And didn't prove this part because we left listrep as a no automatic unfolding during simplification. So let's unfold listrep now. Remember listrep, it was our user-defined thing, and on nil, listrep on nil produces something equals the null val, the null pointer, and the empty footprint. And the something was this second argument. So we have to prove that that equals null val, and we have to be satisfied by the empty footprint. So that's our proof obligation. And we'll just call the entailor-bang again to see what part of this it can simplify away, and the answer is it simplified all of it away. Okay, so we've proved that the current assertion satisfies the loop invariant. Second, we have to prove that the expression can evaluate without crashing. This is usually pretty easy. It's not 100% trivial because the variable we're evaluating has to actually be defined and initialized. Otherwise, that's an illegal operation in C. But the program logic keeps track of what variables are defined and initialized. So we just call entailor-bang, and it solves that one. And that's sort of typical. And now we prove that the loop body preserves the loop invariant. Well, what was that all about? Here was the loop body again. It's T gets V arrow tail gets W, W gets V, V gets T, and that shifts things from here to here. So we have to prove those four statements. And the first statement is T gets V arrow tail. So V is presumably a cons cell, a list struct that we can dereference. And let's look at our precondition, and let's go forward. And forward says, it is not obvious how to move forward here. And why is that? Well, we're dereferencing V, and so we look in here for a maps to that says V points to something that we can dereference, and it doesn't say that. It says, well, V is the address of a list representing S2, and maybe V is nil. So why is V not nil? Well, the loop test said V was not nil. Null. Let's be careful here. Nil is the empty sequence, and null is the zero pointer. So why is V not null, and therefore S2 not nil? It's because the loop test said while V, and the forward while has hoisted that loop test above the line in this form, is pointer V. Let's talk about the val type. Operation of values during the execution of C programs, the things you can hold in variables or in fields of data structures, are either undefined or integer values or long integer values or long float values or short float values or pointer values. So that's just the inductive type that CompCert uses in its operational semantics to represent values. And is pointer simply means it's one of these. And since the null pointer is one of these, then we know V is not null. Okay, let's do case analysis on S2 to prove that S2 is not nil. Okay, so we'll destruct S2. Here's the nil case, right? S2 equals nil. And let's examine that case. Let's unfold this list rep. And it says, well, we know that V is the null val and some other stuff. And when we have a proposition in the precondition of a Hoare triple, we can move it above the line with intros. So there is V equals null val above the line. And now let's do subs to V. And then is pointer null val is a contradiction. And I can demonstrate that very clearly by reducing it to head normal form. H and F in HRE. And it's false. Okay, so that disposed of the S2 equals nil. Here we have list rep of H cons R. V is that address that represents H cons R. So if we unfold that instance of list rep, then we get this. There exists a value y such that V maps to hy separated from list rep ry. And when we have an existential in the precondition, we can move it above the line with intros y. So there's y above the line. And this is one of the important features of verifiable C. The assertions are written with Coq bindings and Coq variables, and the operations of the program logic move those above the line where you can reason about them with all the primitive facilities of Coq. Okay, so now this is what we wanted. This data at that says V does point to H comma Y is what justifies the dereferencing of V arrow tail. And so now we can just say forward through T gets V arrow tail, and forward through V arrow tail gets W, and forward again, and now we're at the end of the loop body, and all that's left is to prove that the current assertion entails the loop invariant. And here's a little ugly thing in verifiable C. The 4 existentials of the loop invariant have been uncurried into a single 4 tuple, which is not beautiful, but that's all right. Let's see if we can simplify this entailment a bit using entailer bang. And it says, well, I simplified it that much, which is a little bit. Now let's demonstrate a value for the 4 tuple. For the new S1, we'll choose H cons the old S1. For the new S2, we'll choose R, the rest of the list. For the new, whatever it was, W, we'll choose V. And for the new V, we'll choose Y. So that just instantiates X, the 4 existentials. And let's call the entailer again to see how much it can simplify. And it doesn't usually take so long. Something about the latest version is making that take too long. Entailer has left 2 sub-goals. One is a pure proposition, and the other is in separation logic. So let's look at the pure proposition that the reverse of S1 appended with H cons R is the reverse of H cons S1 appended with R. And you can see where that came from in reasoning about reversal of lists. We're reassociating the reversed list. So how do we prove that? We enter the mathematics of the application domain, namely the theory of lists in Coq. And we can rewrite, well, let's simplify rev of H cons S1. So that just puts H as a singleton at the end of rev S1. And we can rewrite by the associativity of append. All right. And then that's just beta eta equal. All right. So that was the mathematics of the application domain. Here we have separation logic. We need to prove that any state that satisfies this one also satisfies this one. And for that, it looks like we should unfold this list rep. So let's unfold that list rep. And now we have to demonstrate that there exists a y such that v points to, y naught, such that v points to h y naught. But it's very clear what that should be. It should be w, so that we can match this one. So we'll just say exists w. And then we'll see if the entailer can solve this one, which it looks like it should, because it's just a rearrangement of terms, and it's solved. Okay, and the last sub-goal of the forward while is that after the loop, you have a precondition for the rest of the function body that works. And if you remember the if rule, where was the if rule? Oh no, the while rule. Here it is. In the while rule, we get to assume the loop invariant and the negation of the loop test. So where's the negation of the loop test? It's right here. V is the null value. Okay? And now we have to prove this. And so what have we got? We got a return statement. So let's go forward through the return statement. When you go forward through a return statement, you have to prove that the current assertion satisfies or entails the function postcondition. And what was the function postcondition? There exists an x, a pointer, that's equal to w and that points to, well, it's done some substitutions and rearrangements and has this value. So this comes from taking the function postcondition and doing some simplifications and substitutions in it. Okay, so that's what we have to prove. So what value should we instantiate x with so that it will equal w? I propose w, and then we'll call the entailer to simplify the goal. And so this is what we're left with. And h1 says null val equals null val if and only if s2 is nil. And where did that come from? Well, it came from that v is the null val, and we had something about v. So we know that s2 is nil. Let's rewrite by s2 equals nil right there. Okay, and now this list rep, let's unfold that one. That says null val equals null val and emp. So fine, let's call the entailer to simplify some of this stuff. And now this is what we have to prove. And so let's do some mathematics of the application domain now. Appending with nil is a right unit, right? Nil is a right unit for append, so we'll rewrite by app nil end. And reverse is the identity function, so the fancy name for that is that reverse is involutive. And this is what we have to prove, and it proves by auto. Okay, so our little program on linked lists is proved. We could prove bigger programs. We could prove that, let's see, lots of interesting bigger programs have been proved, like little chunks of OpenSSL and Embed TLS. No really large programs, but some small and actually useful programs. But instead of proving a bigger program, let's prove an even smaller program. And that's this one. So this is the homework, the first homework. And you can find it in this stack chapter of the Verifiable C volume of Software Foundations. And here's our program. There we go. It's going to implement an abstract data type. So if we were doing this as software engineers in C, we would make a header file that exports struct stack semicolon and doesn't tell you what's in a struct stack. So it would be an opaque struct. and we'd execute the function prototype.